Hello, we're going to look at matter which has a mass and a volume. So examples of matter is elements, something like aluminum, and also compounds like ammonia, CO2. Now, matter is something takes up space and it has three different states: ice as a solid, and then liquid water, and gas, vapor. Those are the examples. And when you consider ice, the particles of ice is tightly packed, and liquid water particles are loosely packed. And if you consider a cup of coffee, and then the vapor is actually not packed, they're just chasing away into the thin air, right? Okay. We also want to know the transformation from solid to the liquid. That's a endothermic process, and melting takes place and heat should be added. Same thing, evaporation, heat should be added and liquid goes to the vapor. Cooling, backward, condensation, you need to take out the heat. If you take out more heat, and that would be doing the fusion, and you end up with the ice, right? So the green ones are exothermic, those are cooling processes. Now, if you look at the vapor or gas, it has no particular volume, and then they have a mass and takes up some spaces, right? They're really tiny particles, right? So let's look at the first gas laws because we're going to focus on gases. What's the important thing? Number of moles, temperature is constant in this case. N for the moles and T for the temperature in Kelvin. So what's the relationship? It simply says the Boyle's law is inverse relationship to pressure and volume. Look at this one. You put 1 kilogram trapped air, 2 liters. You increase the kilogram to 2 kilograms. What happens? The trapped air would be in 1 liter, right? So that's the inverse relationship. Lower the pressure, higher the volume. And increase the pressure, lower the volume, right? It's inverse relationship. This is how we write it. P is inversely proportional to V, or we can say V is inversely proportional to P. It's the same thing, right? Now, so we can simplify this one. The proportionality goes to equality with the constant, I'll say KB for the Boyle, right? And we can just cross multiplication, you can get the PV is KB. So that's similar to Y is MX, right? So we can graph it. Why don't we graph these two proportionalities first? Pressure versus 1 over V, actually pressure versus V, and we will get something like this, right? So this one shows inverse proportionality, and this one also shows V versus P, inverse proportionality. So those are the first two that we talked about, right? These two. That's the inverse proportionality. But this one here is Y is mx. So that's we should be given this way, right? So it's a linear relationship, and your y-axis is should be P, and yes, your m, the slope is KB, and your x-axis is 1 over V actually. So we can y is mx is actually P is equal to KB 1 over V, right? So that's how you can show that. So we can also write V is KB 1 over P. So then you just put the axis y and x as you needed, right? So it's a y is equal to mx mx type of graph. Now, so typically we write PV is KB, then we can write a second another stage of the gas, P1 V1 is P2 V2. In this situation, remember, number of moles, the mass, and the temperature has to be constant. Now, so we're going to move to the next law, Charles' law. So in this case, the pressure and number of moles are constant again, N and M and constant. And what's the relationship between temperature and volume? It has to be direct relationship. It's let's see this way: 20 Celsius room temperature balloon versus if you put the balloon into the sunny day outside, what happens? It gets bigger, right? It's going to burst out, we know, but it gets bigger. So that's because it's like 28 degrees, right? So if you put this balloon in the fridge is about 4 degrees. It's colder. You can try actually, right? So it will be shrinking. So that because fridge is 4 degrees, right? So colder condition. So what we see actually, so the size of the balloon, the volume of the balloon keep changing with the temperature. So we have been increasing the temperature. Another important thing, the pressure is constant, atmospheric pressure, number of moles, and the mass gram is constant. But cold, the medium, and the heated temperatures will give you increasing volume, right? So that means volume is directly proportional to the temperature, right? So in this case, the temperature, actually all gas law problems, temperature is Kelvin, right? The heat is directly proportional to volume. So the T, the Kelvin, it's important, only Kelvin you can use, not Celsius. So the Kelvin T is directly proportional to V. We can put a Charles constant, and T is KCV, right? So Y is equal to mx again. So it's a linear relationship. So we can graph it this way. So Y is T, temperature in Kelvin, and x-axis is V. So it goes linear relationship through the 0, 0, right? Okay. Now that's straightforward, but this is the more important part to understand and memorize. Okay, so what's this one? If we graph this one in the centigrade scale, the Celsius scale. So Celsius scale, 0 Kelvin is, 0 Kelvin is actually minus 273. And that should be here, right? According to my graph. Now, look at the 0 Celsius. Is actually 273 Kelvin, right? So that means this graph should go like that. Okay, what's the fancy thing about here? This portion is called the molar volume. So at 0 degrees, 22.4 liter for 1 mole of any gas will have the molar volume. So that's the important thing. There are a few other things. Let's say CO2, you cool it to minus 40 Celsius, it will be solid carbon dioxide. You cool nitrogen to minus 80, it will be solid nitrogen, liquid nitrogen actually, right? So that means no gas ever going to be found in the 0 Kelvin. Nothing exists at 0 Kelvin, no gas, right? So we can simplify our math problems. V1 T1 is V2 T2, right? Now, so Gay-Lussac's law is next one, but it's not widely used, but it's good to understand this depending on your course, right? So in the Gay-Lussac's law, let's see here. Yes, so we can at the room temperature, let's say 20 Celsius, and then you have a balloon and some gas molecules, right? And then you go to 30 degrees Celsius, and then you have gas molecules, right? So what has happened, the same number of gas molecules, that's the important thing here, right? So if it is the same number of gas molecules, and N and Sm, the mass and the number of moles are constant, and pressure is directly proportional to T, the Kelvin, right? So we can say P is constant of Gay-Lussac to the T, Y is mx. So we can write this one also, P1 over T1 is equal to P2 over T2, right? So not very common. So let's look at another one, which is we call the combined gas law. In this case, you're taking all three into one. But let's put another thing. So the Avogadro's law. So this one is basically number of gas molecules, gas moles. Number of gas moles can be shown this way. N is directly proportional to V. That means volume is depending on how many gas molecules you have, on gas moles, right? So V1 over N1, V2 over N2 you can write, right? So it's a similar fashion, but last two, Gay-Lussac and Avogadro, separately you don't really analyze in questions, right? Now, the most used one is combined gas law. That's actually Boyle's, Charles, and Gay-Lussac together. So PV is KB from the Boyles, and then V over T is KC from the Charles, and V over N is KG from the Gay-Lussac. You put everything together. So KB, KC, and KG is one big K constant. So we can write PV over T equals to one big constant, whatever Boyle, Charles, Gay-Lussac, right? So that it is that one K. KB, KC, KG, it's one big K, whatever, right? It's a number, numerical value. So we can write P1, V1, T1 is P2, V2, T2. That's the most common one you're going to be using, right? Now there is another thing that some of my students use most of the time, and sometimes it's helpful. Look at this one. Can these guys possibly be Victorians? So let's see how you use this one. It's a way that if your prof is not giving you the formulas, you can memorize it. So can for Charles, these for temp, Kelvin, and temperature Kelvin, right? And guys for Gay-Lussac, and possibly for pressure, and B for Boyles, and Victorians for volume, right? Now, how do you put this one together? If you're not given a formula sheet, you have to memorize it. You draw a triangle and cut into three like this, and then you start from there. Right middle corner C, T, G, and P, B, and V, right? That's basically the can these guys possibly be Victorians, right? Now you put the corners into the each cage, each corner, right? So that means you can put the T here, V from there, T from here, and P from here. So that's it. That's the one. You can use it for any of the rules to be taken out from it. So P and V. So if you go horizontal, you get the P1 V1 is P2 V2. You go vertical, you get the P V over T, V1 T1 over V2 T2, or you can go to get the also you can get P1 V1 T1 is P2 V2 T2, which is the combined gas law, right? So you can pretty much memorize everything on this one. Thank you.